let's look at this carcass data set. It's a data set that's in this package, GRBase, that contains measurements of the thickness of meat and fat layers at different locations on the back of a slaughter pig. And so we've got 344 carcasses. And we use it to predict, we could use it to predict lean meat percentage on the basis of thickness. So we've got what is supposed to be a matrix. I was thinking that maybe I could fit this thing, but I don't think it will do for me. But and you're supposed to, this is just the data itself, the GRBase data. And so what we're going to do is we're going to consider a normal, consider the data to be normally distributed, so some mean, some covariance matrix. And basically these Gaussian graphical models are a way to understand how variables are mutually related. The same thing, conditional independence. And here's an actual concentration matrix, not the data itself, but what we most care about when it comes to Gaussian graphical models is this concentration matrix, or the inverse of the covariance matrix. Like this is it. Like if we can figure this out, then we can construct our graph, basically. And the reason is as you know, the partial correlation of two variables given all of the other ones is this, which is constructed in terms of that inverse covariance matrix. And if we have a 0 here at this, in this numerator, then that means those two variables are conditionally independent given all the other variables. So that goes right in line with our same conditional independence when it comes to graphical models. And you can construct the graph, basically find those zeros and ones, or just zeros and non-zeros of your off-diagonal elements of that inverse covariance matrix. So, the diagonal elements, you're not looking to be 0, but these ones, if you have any zeros or non-zeros of any of these off-diagonal elements, and you only care about half of the matrix because it's symmetric, that tells you how to construct your graph. If there's a 0, you won't have an edge between the two nodes, and if there's a non-zero, you'll have an edge between those two nodes. So does that make sense? That's pretty much what Gaussian graphical models is. Like if you can figure out this matrix and get your zeros and non-zeros, you have your graph. So we can make our concentration, we can estimate it. There's different things you can call. So I can send out the presentation that you can find in R, and you can actually see the code in it. This calls, I can't even remember what this is calling, but you can call a function that creates a concentration matrix, and you can, instead of using a concentration matrix, you can convert it to a correlation matrix. So that's what this is saying. You might have different scales then, because as you know, partial correlation is invariant to scale. So you might consider that instead, and it's the same thing. Like with this equation, partial correlation, inverse covariance matrix, the relationship is exactly the same. So this is telling you covariance to correlation will give you a matrix like this, and if we were to look closer, we would see like small correlations between, say, lean meat, relating to lean meat. So those small correlations are ones that we might leave out. So fat 1, 3, it looks like it might be conditionally independent of meat 1, 2, given the remaining variables, and lean meat might be conditionally independent of meat 1, 2, given the remaining variables. So maybe meat 1, 2 is something that we don't need, especially if you're interested in lean meat or fat 1, 3. And again, this is specific to that data set, but this is how you might go through and think about your variables, the ones you're interested in, which ones seem to be conditionally independent to the ones that you're interested in, especially if there are multiple ones. Like meat 1, 2 is conditionally independent of a couple of different variables that maybe are of interest. So if you want to predict lean meat, maybe you don't need meat 1, 2. So you can use like a stepwise backward selection method, basically to prune. I'm using the word prune even though I don't know if that's the terminology, but to go from a dense graph where you just have all edges, like what's called a saturated graph, to remove some. So maybe those little ones, like that meat that meat one too is one that might be removed because it's just got those little partial correlations. You can use something like a AIC to do model selection. So that's what this is doing. It's calling AIC, and we get a graph that looks kind of like this. So it's not the best looking graph, but with this PDF. But this is lean meat. This is fat 1.3, meat 11, fat 1.1, meat 13, meat. I think that's meat 13, but this is what it would look like if you used, say, stepwise. And then you can also use BIC to prune or to construct a simpler graph from a saturated graph. BIC yields a higher penalty. There's an extra log n term on that BIC, so it will give you a simpler graph than AIC, which you might want. So these are things you think about, like, do I want a graph that has more edges or less edges? Like maybe you want to pare it down just to get just those really strong, I call them signals between a certain variables, or maybe you want a more denser graph and you just want to see what's happening. You don't really want to remove something that may be of interest. So you can decide. And so BICs, this is what that would call, and so it removes edges between fat 13 and meat 13, and lean meat and meat 13. And so that's what that one looks like. So, I mean, you can, even though you can't really read the names, you can tell that it is a simpler graph. There are less edges. And so that's kind of nice. It's good visually to see something simpler than more complicated. And we always, we tend to like things to be more parsimonious, so, as statisticians. So sometimes that's a good thing for us. So, so this is saying GGM using BIC, and so we've got two clicks. We've got this one and this one, and from here we can tell that lean meat and fat 13 are conditionally independent from meat 12 and meat 13, given fat 11, 12, and fat 11, fat 12, and meat 11. So I'll show you. So this is lean meat and fat 13. This is meat 12 and meat 11. Meat 12 and meat 13. And this is meat 11, fat 12. So this group is conditionally independent of this group given these. So that's exactly how you might read a graph like this. I mean, all these edges, there are lots in there, but if you at least group them like that, you can really get a concise statement. And lean meat might be something that, that might be a response variable or something. So that might let you know that, okay, if I know these variables and these variables, then maybe I don't need to know meat 13 and meat 11, or meat 13 and meat 12. So, does that make sense? All right.
So, is that kind of like two stages of variable selection that you're looking at there, one with the conditional independence part and one with the BIC or AIC that's used?
Yeah, I guess so, because, yeah, so I guess what you could do is, I guess the naive approach would be to go ahead and just calculate that inverse covariance matrix, forgetting about how small or large those off-diagonal values are, and then you would do model selection, or you would use like AIC or BIC to tell you, like, okay, this one's super small, like you could just get rid of it, like just call out a 0, and some of the other ones. So yeah, so
you would just sort of done like a hard threshold of if it's below
right.
something and get rid of it, and then
yeah.
But AIC would have gotten rid of it.
Yeah, exactly. Yeah. And that's up for debate. It's kind of an active area of research. Like you can do thresholding, like you mentioned. You can do AIC or BIC. There's graphical lasso, which I'm going to get into a little bit later. There's all kinds of ways to try to pare down a saturated model to a dense, like a simpler model. And some ways might be better or more consistent than other ways, and that sort of thing. Okay, so this is another data set, body fat. And so we're looking at the percentage of body fat for individual based on simple measurements. This is just a little bit of what the data looks like, even though we can't see it. So they removed errors. So I just put a slide in here of some error, some data cleaning, and we also do a little bit of transformation. So we get a partial correlation matrix that you can call you can first do your covariance, inverse covariance estimate, and then convert that estimate, inverse covariance estimate, to a partial correlation matrix. So that's what this is doing. And there's a high correlation between body fat, a high partial correlation between body fat and abdomen, which if you were to see it, it would be like 54. Like, it's pretty large. So we can fit another model using stepwise selection to pare it down, and we get something that looks like this. So again, it's super hard to see, but these are all of the different variables in the data set. And so that's actually with BIC. So that's actually a simpler graph. And so it has all of your variables as direct predictors except chest, knee, and biceps for body fat. So if we were to zoom in on body fat, we would see that there is no edge that connects body fat to chest, knee, or biceps. And we can also see how many edges are in the model. So there are 61 edges. So that's the idea. And like I said, I'll send this to you so you can actually see things better than what this presentation is showing you. All right, and so that's really the idea of Gaussian graphical models. You know, I'll just kind of reiterate that we've got this graph. We've got a Gaussian distribution where we look at those off-diagonal elements being equal to 0. That means in that inverse covariance matrix, that means there's no edge, and that is our dependence graph, because if there's no edge between two variables, then those two variables are conditionally independent given all the other variables in the model. And so again, we can factorize our undirected graph, and because of that, we can factorize it according to cliques. The global Markov property holds, which again is just one of those tenets that's really important for us because it basically sets the foundation for all of the analyses that we use.